Is this where we left off at?
A little further down, the next paragraph. Oh, wait, what specific sample mean?
It's right. You're right.
Oh, the second paragraph.
Yes.
I got you. It helps if it's connected. If you like plug it in. Like it.
It talks to me, says it's computer ready to record. Cool. Right. That's what it felt like. All right. All right, so we're on this paragraph. Okay. All right, so when a specific sample mean, which is this little annotation here, is chosen, there's a 95% probability that the interval, and it uses the appropriate mean this time. Just can't, right? Yeah, I don't get that. Why? I guess it's that one area. Plus or minus the 1.96 times the standard deviation of the population divided by the square root of the sample contains the sample mean. And there is a 95% probability that the interval specified by this result will also contain this mean. So basically, again, we're finding an interval where basically you can go both ways. Is if I take a population or sample out of that population, my mean will fall in this interval, and I'm 95% confident in that, meaning 95% probability it will. There is that 2.5 on each side that it won't, or vice versa. I can do all these sample means, and after looking at my numbers, I can say the population mean will fall between these two intervals. So it can kind of go both ways depending on what you're trying to find out. So again, that goes back to the correct notation. If the population mean is known or unknown. Sucks getting old, guys. Stay young. I feel like a flashback just happened and then coming back in. And really what it is like there's a third wall that's being broken on what actually happened this weekend. And it's like, if they only knew. All right. So anyways, it's I don't even know where I'm at in my notes. All right. So so basically this is your range, whatever your result you get here in here, this is your interval, and your population mean will fall in that interval, and you're 95% confident in that. They are constructed for all possible sample means, with the sample mean, again, you're 95% of the intervals will contain the population mean. And so it's basically the same thing we just keep saying in different words, it seems like. All right, so the confidence level determines the critical values of Z. Remember, that says how many standard deviations from the mean you are that are used to find the confidence interval. And we'll use the table E, not technology. You get to use the table to on the test. So practice, keep using the table E to find the critical values that you'll be doing this plus or minus with. So the Z-score, where it's alpha divided by 2, this just simply means the alpha divided by 2. If I'm at 95%, my alpha would be my leftover percent, which would be what? 5%. But we divide it by 2 because it's on each side. So that means there's 2.5% on each side. So we would be looking for like 0.025 as the area on this side, and then the positive version over here. And so that's how we can find it. And that's actually how we got the negative 1.96 to 1.96 in the previous unit. All right, so that's what this right here is representing, and it says it again. Alpha represents the total area in the two tails. So remember, the probability or the confidence is your area. So that 95%, it's the same thing as 0.95, which is the area under the curve. So the alpha divided by 2 represents the area in each tail. So if I have 5% left, that means each tail would have 2.5%. The confidence interval level is the alpha. Thus, when 0.01, then 1 minus the alpha would be 1 minus 0.01, which means that you are 99% confident in it, and your alpha divided by 2 would be 0.05%. Sorry, 0.5%, which will turn into 0.005 as the area. Right? So I would have to go look for whatever that area is, and I don't remember. Actually, you're about to find out in the chart below on what that is. Questions on what this means here or any of this? So your alpha is going to be your percent or your probability or your area under the curve. Subtract it from 1 to see what you have left over. Divide that by 2. Then that will tell you what area you're looking for on the left. And it's just going to be the positive version on the right. You good with that? Okay. We'll definitely do some examples. Did y'all get a table? You get the table later. Just making sure y'all got the table. All right. There is a margin of error that we need to talk about as well. Oh. So the term E here is equal to whatever that Z-score of half of the theta is. So remember, that would be like, if it's 5%, that would be 2.5%. So that would be the area 0.025, which we know is 1.96. That's what this result is, times the population standard deviation divided by the sample, the square root of the sample. We good with this? On what all these letters mean now? Doesn't look so foreign. Go ahead. The N, that is your sample space. So like if your population, let's say we don't know the population, but let's say this is entire school, well, we're going to grab 30 people. N would be 30 because I'm going to grab, that's my sample. That's part of the population. So you'd be square root of 30 as your result, or whatever the situation might be. And again, this right here is called the margin of error, or also known as maximum error. These type of notes right here are great true or false questions or fill in the blank questions. So when you're studying for the next unit test, pay attention to these type of questions or notes. All right, and so again, this is the maximum error of an estimate. It is the likely difference between the point estimate of a parameter, which again is the population, and the actual value of the parameter. All right, so we get an estimate of what's happening in the population, and we hope it's relatively close, but it'll be the difference of what actually happens. So we'll do all our math. So we'll probably do the entire population, and we'll see just how far our margin of error is. The smaller it is, the better off you are. The larger that is, the less likely you're going to get hired. So you want to keep your margin of error as low as possible, and we'll calculate all that as well. So here's a couple more definitions. The margin of error depends on the following factors. Population standard deviation. So the normal distribution can be used to find the confidence level when the population standard deviation is known, but really the only thing you need to take away from this is the population standard deviation. The confidence interval, so whatever you get in that range. whatever you calculated in your range there, and then whatever your sample size is. So whatever that little n is, all of those has a factor on your margin of error. We'll go with this. These little blanks here are the equation, which again was z alpha divided by 2 times the standard deviation divided by the square root of 10. This is still actually 7.1. This video may or may not have sound. Needs to be working fine. All right, so again, this is the confidence interval. Do what? Yeah, roll point. Yeah. All right, so yeah, true. Yeah. All right, so 7.2 confidence interval for the mean. This right here we know should be that guy, because it's wrong notation there. All right, so here we go. So assumptions for finding confidence interval for a mean when. See, but this says standard deviation is known. But then earlier, what was the mess up yesterday? I thought so too. The best point estimate of the population mean. And this says finding a confidence interval for a mean. Maybe when the standard deviation is known. Maybe that one piece was false. We'll keep it as is for now. And see if y'all see a connection. Because this says find a confidence interval for mean when the alpha. Oh, that's an alpha. When alpha is known. Yeah, and this one says confidence interval for the mean when standard deviation is known. That still seems like a complete sentence. So I'm going to keep that as is. I'm thinking the other one, maybe the wording was wrong. I am too. The math shouldn't be confusing, but this little notation here. Yeah. All right, so there we go. So to start off, assumptions for finding a confidence interval for mean when alpha is known. The samples are going to be randomly selected. The sample size must be at least what? 30. From yesterday. Yeah. At least 30, or the population must be normally distributed. And it only has to be normally distributed if your sample space is less than 30. If it's more than 30, it does not necessarily have to be normally distributed for us to calculate our interval. If it's less than 30, you have to be told it's normally distributed. Okay, that's a big fact there. So even with these assumptions, keep in mind there will always be a chance where alpha that the confidence interval may not include the true population. That is why statistics we're never 100% sure about anything unless we're 100% sure that it's not going to work. That's about as far as we can go. Like, what's the odds that you're going to land on a 7 on a die? Not possible. So we're 100% positive that that's not going to happen, right? Some there are. I am thinking there's no 7 on a die. Go ahead. We're only 100% confident when we know it's not going to happen. Yeah. But we're not going to say we're 100% that's going to happen every time. Not necessarily, no. We're not going to say 100% though. We would say more like we're about 99% sure if we roll the die forever, we should get a 6 at least once. Yeah. We got to keep it that margin of error in there for us. All right, but this is what I was talking about with the chart. This is going to be very important. You can always calculate these. I'm going to be honest with you. I always remember this one, but I had to always calculate. Well, my bad, not that one. Always remember this one. But I had to calculate the other two because I would always forget. But if you can remember these are going to be the z-scores. You're always going to be working. We're usually always working within 90, 95, and 99 percentile or percent confidence. There are some times that the test likes to throw, or maybe in a test question or a homework question might be like, hey, we want to be 80% confident, then go calculate it and then know how to do that. But these are going to be the 3 z-scores that you're going to need to know. And remember with these z-scores, this really should say plus or minus because you have to go get that negative version. So remember this right here, the alpha would be 10, but then that would mean that alpha divided by 2 is 5%. You're looking for the area at 0.05. And at that is negative 1.65. If you don't believe me, you can check it on table E. And then if it's negative 1.65, the positive 1.65 will have the same area over there. That's kind of how all these numbers came to be. Is that making a little bit more sense? These numbers didn't just come from thin air and we were like, these numbers look really nice together. So that's not what happened. This came from actual calculations. Looks like our first example is finally coming up. Time to do some math. All right, so example 1, it says number of jobs. A sociologist found that in a random sample of 50 retired men, the average number of jobs they had during their lifetime was 7.2. The population standard deviation is 2.1. That's a lot of jobs. I guess in 50 years, you probably only started working when you were 16. Yeah, but I mean, to have 7 jobs, that doesn't seem like you're staying at your jobs very long. Yeah, that's what I fear for y'all. Because y'all are like, I get some of the students will be like, yeah, I quit this job. I was like, didn't you just start there like 2 weeks ago? Like, yeah, but I didn't like how they talked to me. I was like, okay. And they're like on their 5th job and they're not even out of high school. And I'm just like, had 1 job in high school, did that for 3 years, and then transitioned into the real world. I realized blue collar wasn't my thing. I think I have more room down here, huh? No, I was a carpenter assistant. Yeah, worked for we built cabinets and countertops and stuff like that. Does it give you the answers on y'all's? No, but I could have. Well, that stinks. All right, we'll talk about it then. It doesn't look like it does all of it. All right, so on part A, it says find the best point estimate of the population mean. And here it says the best point of population mean is the sample mean. So the best point of estimate will be whatever the population mean is given. And it's given to us as 7.2 because they had an average number of jobs. So remember, average is the same thing as mean. So when you're wondering how they got this 7.2, they pulled that from the description where it said the average number of jobs they had during their lifetime was 7.2. So that's your best estimate for the population mean, because it's really and truly your only information given with these. Oh, they're just 50 retired men. Man, I read that completely wrong. I was thinking they were 50 years old. So they're retired and they're, yeah, so they're probably like 62, 65, something. Yeah, okay. So 7 might not be so bad. Okay. All right. So then the next part says find the 95% confident interval of the mean of the number of jobs. So the way we're going to do that is we got to calculate what this part is. So we got our mean of 7.2. This guy, again, if we're doing 95 percentile, so this is 95 percentile, my alpha would be what? What's alpha? It's the leftovers. So what is it? It's going to be the 5%. But then the alpha divided by 2, that would give us the tails. That would then be the 2.5%. Yes, instead of it being worked out for you. All right, now with that said, this is a percent. We need to turn it into an area. So for that, that's going to be 0.025. So I want you to verify these numbers. So use your table E real quick and tell me what the z-score is for 0.025. Point 0.025. Perfect. Which is exactly what, yeah. No, she did. No. But but you can see that that was the result we kept on getting beforehand. So now you can verify that table E did give you these answers. And then when you do this enough times, you'll be like, all right, if this is 95 percentile, it's 1.96. 9 percentile, it's 2.5. If it's 90 percentile, it's going to be 1.65. Whatever the situation might be, then you already throw that out there. It just gets different if they want to be complicated and go, what's 82.5% confidence interval? Like, no one does that, but you would calculate it this exact same way. All right, so with that, to calculate this, we're going to now do so the math here. This would be 7.2 minus 1.96 times, what was the standard deviation they gave us? 2.1. What was my sample size? 50. Perfect. And it looks like it has the mean. There's a typo there. This should be a less than right here. All right, so in y'all's calculators, let's calculate this. You know what market is missing in this town that y'all should try to do? I feel like we're already kind of a fishing community. Lower gas prices would be nice, but that, yeah, I missed the mark there. I was I was thinking more of like the food people that drive by and give you food, like you pay them and they're like the curbside or DoorDash, yes, like Uber Eats or whatever. I think you could. Oh, yeah. I don't know. I don't know. That's for you to figure out. Like, and I think it'd be a great thing for y'all to do because I would pay for it. No. How would y'all calculate? 617, so 6.2. Okay. Now we're gonna do the same thing, but we're gonna do a plus sign. So you can copy and paste your formula you just put in, just change the minus to a plus. Y'all remember how to copy and paste? So you just hit the up button until you highlight it, hit enter, it copies and pastes it. $9.16. Perfect. And if you kind of look down in your, ooh, you might want to check that. You might want to check it. Oh, you can't just do that. You have to do 1.96 times 2.1 over the square root. Again, if you just hit the up button, highlight it, hit enter, just change the minus to the plus, it copies and pastes. You already got it? Okay. No. Me too. It is on the paper. All right, good. So therefore, you know you did it correctly, and now you do know how you did it. So what we just did here is you basically just found All right, so what this basically means here is you are 95% confident that the population mean of all of these retired men would fall between 6.62 jobs and 7.78 jobs. So that's what this basically means. And you might find some random retired person that has less than 6.62 or more than 7.78, but we're thinking that's going to be about 5% of your data. When I say that, hold on, let me back up there. It's not one random person. It's a random of a group of them, which is 30 or more, right? So if I grab a 30 or more and then I find their mean, I'm 95% confident that it'll fall between these two means here, right? All right, so if we look at C says find the 99 percentile. So again, I want to go through the process of calculating it. So if I'm looking for the 99 percentile, what is my alpha going to be? 1%. Therefore, what's my alpha divided by 2 going to be? Whoa. You mean like 0.5%, right? And then if we talk about Z-score, now you're talking about 0.005? Okay, cool. All right. Look for the Z-score at 0.005 for me in your table E. What is it? All right, so here you go. So that is how they calculate. So Rivers, you can verify that it did work. Other gentlemen, make sure that these work and you know how to find it just in case it gives you a weird one. we're gonna do the same process. You're gonna take the 7.2, subtract it from 2.58 times the 2.1 over the square root of 50. Figure out what that is, and then do 7.2 plus 2.58. 2.1 over the square root of 50 is. So if you're trying to fill out these notes, what is 2.58 times 2.1 over the square root of 50? No, just that part. Okay, we'll talk about the final answer here in a second, but what's just this part? In your head? Good. So 0.766, we'll just say 0.77. But then the final answer, the 99% confidence interval would be what? And what's the right side? And you can just copy and paste it and then hit the up button until you highlight it and hit enter. All right. So now what we're seeing is now we are 99% confident that all of my sample means or range. Notice when your confidence interval increases, our interval range also increases because we're more confident because we can fit more data inside it. All right, so that's what's happening. I was like, I don't even know what we're going to talk about tomorrow. You're like in the future. Wider. So the bigger your first confidence interval, the wider your interval is. Yeah. Okay. But I do know when I was in your shoes, I got confused a lot as well. So the more the wider, it's why you're more confident. Yeah. I didn't either. All right. Part D, which is smaller? Like what is smaller? It doesn't even says which is smaller. The confidence interval or the percentage? Because yeah, but the directions part D just says which is smaller. Explain why. What do you mean which is smaller? I'm going to go with the confidence interval. So which one has a smaller interval of numbers? The 95% confidence interval. I guess that's what it meant. I didn't take that from the directions. But the 95% confidence interval is going to be smaller. Then you can say along the lines that because the interval of numbers, or I say that, the range maybe, the range of the interval is smaller. Questions? All right, that's good. All right, sorry, I was just thinking. So looking at the second objective here, it says determine the minimum sample size for finding a confidence interval for the mean. So we talked about sample size first. So the answer to the question, how large a sample is necessary to make an accurate estimate, is not simple because it depends on the margin of error, the population standard deviation, Now it's using the right vocabulary. And the confidence level. So that's what it depends on. So if you wanted to solve this out, we're going to solve for n. So we're going to do a little algebra. Let's see how good y'all's algebra skills are still. What would I do to this literal equation to solve for n? What would I have to do first? What am I doing? Am I multiplying or dividing? Okay. I'm going to divide by this z alpha divided by 2. This is actually one thing. It's just a subscript here. So this, again, is just one thing. This is not like multiple things. Yeah. This is what we did in college algebra. Finding n. You could do that. So if you kind of recall proportions back like in algebra, if I multiply by the square root of n over here, what then am I going to have to do with this guy? Bring it back over, and how would I do that? Multiply by what? Okay. And then you divide by what? Okay. So let me just start off. We'll multiply by the square root of, right. What's that called? So if I'm going to divide by the e and multiply by the z, if I want to do it at the same time, that would be multiplying by its. So I'm going to write it out for you. Okay, what's that called? Nope. So I'm dividing by the e and I'm multiplying by the z. What is that guy called? Yes. So you can multiply by its reciprocal. And now I have something that looks like this. Well, I knew y'all knew. Where did this come from? Oh, I was like, where did I come from? All right, well, no, I was like, I don't know where I came from. All right, anyways, and then what's my last step here? Square it. You now just developed an equation of what your sample size has to be given certain information. So if I'm given my margin of error, I'm given my population standard deviation, and I'm given my confidence interval, basically I would have to find, like, if it's 90 percentile, then, or 99%, I would have to calculate what that z-score is, right? No, E is the margin of error. So E, margin. So that's margin of error. This is your population standard deviation. I'm just gonna do that. And this, well, I guess that defeats the purpose of me writing this out, doesn't it? Standard. And then this right here would be your confidence interval. But you don't need like all of it. You just need the z-score. Right? And again, this is going to be squared. So it's not going to matter if you choose the negative version or the positive version, because regardless, a positive and negative squared will still give you a what? A positive. So you don't have to worry about choosing the left side or the right side. You can use either one. When you plug it all in, it'll all give you the same answer. Okay. So we're good there. So if you need to know how large your sample has to be to have all of this work out for you, you would need to be given those three things. And they actually produced the formula for us in our notes right here. So it's a nice cleaner format. So you don't have to try to read your teacher's writing. And again, it also, if I just kept on reading, explains what E is. And then it just says round to the next whole number since the sample size must be a whole number. So basically, if you get, I don't know, 42.3, you need that 0.3 of a person. So just go ahead and round it up to 43. All right, always round up regardless if it's 0.5. We all good with that? Okay, let's look at an example with undergraduates. All right, so in example 2, we're looking at undergraduate GPAs. It says how large a sample is necessary to estimate the mean GPA of each undergraduate class at a large university with 0.25 at the 99% confidence level, where the population standard deviation is 1.2. So if I want to calculate this in, it tells me it has a large enough to estimate the mean of each undergraduate class at within. So when you see that within part right there, that's your margin of error. Typically what you see here, when you do the math for a company, it'll be like plus or minus. So you can be 0.25 up or down, but be within that range. And then we have our confidence interval at 99. So what is that Z alpha divided by 2 going to be at 99 percentile? 2.58. Use that chart, but try to memorize that chart. If you don't get it memorized by the test, you now know how to look it up on your table E. You can always do it that way as well. Remember, at this point, I'm looking for that error at 0.005. It would be 1% divided by 2 is 0.5%, turn into a decimal with 0.005. So if you forget, you can always do it that way. We good with that? And it doesn't matter if it's positive or negative. I just like to stick with positives so I don't like lose anything. And then, of course, it gives us the standard deviation. So now that we have all of our information, we can just plug it in. And you can see that they did that. They did 2.58 times 1.2 divided by 0.25. You work all that out. PEMDAS tells us to multiply, then divide, then square the answer. So they got 153.363. But notice that this 3 in our normal rounding would tell us to do what? But you need this part of a sample. So you will always round up. So this becomes unique for this to work out. For you to have a margin of error that's plus or minus 0.25, be 99% confident in your population mean that you would get, and have a at least 154. Yeah. I heard she keeps talking. I don't know what she said. Disconnected, connected. So I'm gonna say you might get some part in this. So again, so you need 154, but yeah, round up would be a good true false question. She just started talking. Any questions on how to utilize this equation? So if you're trying to find your sample size, you need these 3 things. Right? Without it, you don't have enough information. Another true false question. Or maybe just a multiple choice, doesn't have enough information. All right, note when using technology, use more decimal places than specified in rounding rules. Don't round during the process, round at the end of the process because you don't want to get a rounding error. All right, in your notes, this says 7.3 confidence interval for the mean, the population standard deviation unknown. This is actually going to be 7.2. And what time do we got this class? Okay, we got about 5 minutes. All right, so then objective 3, it says find the confidence interval for the mean when the population standard deviation is unknown. Again, I feel like they're using the right stuff. I just think the first page was a little off. Most of the time, the population standard deviation is unknown. You usually don't know this information in the real world. So it is estimated by the sample standard deviation. So we'll use some sample standard deviations. When S, again, sample standard deviation, is used, especially when the sample size is small, critical values greater than the values of that Z-score of your tails are used in confidence intervals in order to keep the interval at any given level. These values are the student distribution, often called the T distribution. So this is important. This is when it's getting to that point when you're trying to find the confidence interval and you have certain situations. Here's your first situation. T distribution. All right, let's look at what happens when we have a T distribution. So the assumptions required to use this. This is how you'll know if this is the process you'll use to find your confidence interval. Samples must be simple, randomly sampled. Right? So that key word there, they must say that it's simple, randomly sampled. There's no like double blind or whatever. It's just simple, randomly selecting people. The population from which samples are selected must be normally or at least approximately distributed. Right? So we have to be at least normally distributed, has to be completely random or simply random, or the sample size must be 30 or more. And so if it's greater than 30, it doesn't have to necessarily be normally distributed. This is your classic interval stuff that we've been doing. This is called T distribution. We'll go with this. Okay, properties of the T distribution. The T distribution is bell-shaped. The T distribution is symmetric. About the mean, median, and mode are equal to 0 and are located at the center of the T distribution. The curve approaches but never touches the x-axis. The standard deviation is greater than 1. The T distribution is a family of curves based on degrees of freedom. And we'll talk about this here in a second, which is related to the sample size. And the last one, as the sample size increases, the T distribution approaches the standard normal distribution. So this is for number 6, and this was for number 7. Oh, good. We're about to leave. All right, this is a good place to stop, and we'll look at what the bell curves can do. We'll talk about that key thing that you haven't seen before. Where'd it go? Degrees of freedom. Y'all enjoy the rest of y'all's day.